This talk is really about the structure of matter, and in particular about the structure of the protons, neutrons, and atomic nuclei that make up the majority of the visible matter in the universe. Now, our modern understanding is that the protons and neutrons, here inside the atomic nucleus, themselves have substructure, so they're made of matter particles called quarks, held bound or glued tightly together by the force carriers of the strong nuclear force, manifesting as force-carrying particles called gluons. To the best of our understanding, that's it. The quarks and gluons are fundamental particles, and there are no deeper layers of structure. So the quarks and gluons and their interactions are encoded in the standard model of nuclear and particle physics. The framework was put together in the 1970s, and it contains just 17 fundamental particles. You can see them here on the slide. The matter particles, called quarks, which come in different types or flavors. The leptons, like the electron and its neutrino, and their heavier cousins. And force carriers for 3 of the 4 fundamental forces, so notably excluding gravity, which is described by the separate theory of general relativity. We have the photon for electromagnetism, the W and Z bosons for the weak nuclear force, the gluon for the strong nuclear force, and of course we have the Higgs boson. Now, the standard model brings together these particles and their interactions in this very elegant, very symmetric, very predictive framework. And in fact, a number of these particles were predicted from the symmetries and structure of the theory long before they were seen experimentally. So just the most recent few, if we go back, the W and Z boson, that was I think 1983, the top quark, 1995, the tau neutrino, 2000, and then the Higgs boson in 2012 was the last piece of this puzzle to be seen at the Large Hadron Collider. Now, as I said, this is a very beautiful, extraordinarily successful physics theory of the fundamental structure of matter. And I want to give you just sort of a visceral feeling for just how successful this theory is with a couple of examples. So here what I'm showing is the magnetic moment of the electron. That's the torque an electron feels when you put it in a magnetic field. And this is the most accurately verified prediction in the history of physics. So you see here agreement between theory and experiment to 12 significant figures. Now, what I'm actually showing here is called the anomalous magnetic moment. That's just the deviation from the classical result, or the difference from a tree-level result. And this theory prediction here, now that was really a Herculean effort. That's something like 30 years of effort, 12,000 of these diagrams. They're called Feynman diagrams, up to 5 loops for anyone who's into quantum field theory. And yet, beautiful agreement, right? Really quite astonishing. And it's not just quantities like this. This is a, if you like, simple static quantity. The standard model is predictive over an incredibly wide range of energy scales. So here I'm giving you just one more example. This is called deep inelastic scattering. I fire an electron at a proton and I break the proton apart. And we'll talk more about that process later. But that's described in terms of quantities called structure functions. And here on the horizontal axis of this figure, this is energy, and it's a log scale, so this is over 5 orders of magnitude in energy. The dots are experiment, the bands are standard model, and you see beautiful agreement over this incredibly wide range of energy scales. Okay, so the standard model, as I said, is beautifully successful. We also know it does not describe everything we observe about the universe. Right? Just one example, and we'll come back to this one also later, is dark matter. In fact, the standard model describes this slice of the universe's energy density pi, about 5%. About 5 times as much as dark matter, which seems to interact like matter gravitationally but doesn't emit or absorb light, so it's dark. That is not standard model matter. The rest is dark energy. We don't know what that is, but it's whatever's driving the accelerating expansion of the universe. Right, so our beautifully elegant, predictive, symmetric theory describes just this piece of the pie. And it's not just that, right? Neutrinos, we know they have masses in nature. They don't in the minimal standard model. There's a matter-antimatter asymmetry we can't quite understand. If you start from a big bang and create equal amounts of matter and antimatter and allow it to annihilate through only standard model interactions, well, then we shouldn't have quite so much matter left over at the end. Stars, planets, we're all made of matter, not antimatter. We can't quite understand that. Gravity doesn't fit in. How do we unify the standard model with general relativity? There are naturalness problems. Why is there such a discrepancy between the weak and the gravitational scales? Right? So there's lots of reasons we know the standard model is not complete. And so we invest huge amounts of effort as a physics community to try to find and understand those places where our understanding breaks down. So just one of many ways we do that is through experiments at what's called the intensity frontier. So this is a class of experiments that are very precise, looking to find, say, very small deviations from standard model physics. Now, before, I showed you the magnetic moment of the electron as the most accurately verified prediction in the history of physics. The electron's heavier cousin, the muon, also has a magnetic moment, and there's a very interesting tension between the best theory value for that quantity and the best experimental value for that quantity. That may or may not be a hint of physics beyond the standard model, right? Other types of quantities or experiments that fall into this category are dark matter direct detection experiments, where we bury a detector deep underground and look for the potentially very weak interactions of dark matter with that detector. Various neutrino physics experiments fall into this category, and so on. Okay, and something that all of these ways of searching for and constraining physics beyond the standard model have in common is that we need to understand the standard model in order to be able to do them. To compare theory to experiment, you need the standard model theory. To be able to say what you're learning from dark matter hitting a nucleus in your detector, you need to understand the properties of that nucleus from your best fundamental physics theory, right? So understanding from the ground up, mathematically, from the standard model, the structure of matter is important for this reason, as well as for the sort of first reason, the underlying reason. Just can we understand how all of the complexities of nuclear physics come out of this beautifully elegant, in some sense simple, fundamental theory with 17 fundamental particles? So those are really the twofold motivations of saying, let's start from this definition of the structure of matter and work our way up as high as we can. First, for its own sake, can we see the emergence of complexity in nature? But secondly, because we know this theory does not describe everything we observe about the universe, and we want to find where it breaks down. And to do that, we need to understand our theory first. Okay, so that's really the motivation for the quest to understand the structure of matter from the standard model. And I'm going to give you some flavors in each of these two categories, sort of focusing on our pressure. We're in the matter under pressure series, so I'm going to focus a little bit on questions of pressure. But then at the end of the talk, I'll come back and give you also a hint of how recent advances in algorithms, especially machine learning, are feeding back into this cycle and allowing us to change the horizon of what we can do. Okay, so a little bit more introduction. To talk about the structure of matter from the standard model, we have to talk about the strong interaction part of the standard model, which is described by the theory of quantum chromodynamics, or QCD. Now, the strong interaction is responsible for binding quarks and gluons into protons and neutrons, and for binding those protons and neutrons into nuclei. So, of course, it's relevant if I want to talk about the structure of those protons, neutrons, and nuclei, right? Unfortunately, it's also quite difficult to study from theory, especially at low energy scales, and that is because the theory is non-perturbative. So what that means is illustrated here. This is the coupling strength of this theory, the strength of interactions. On the horizontal axis is energy. As I move to the right of the plot, that is to large energy scales, the coupling becomes small, and that means I can expand in powers of that coupling. You square a small number, it gets smaller still, right? So I can expand in powers of that coupling, calculate to some precision and stop and know that the corrections are small. As I move to the left to low energy scales, in fact, further to the left than this plot shows, that coupling becomes large. I can't do that anymore. Why do I care about low energies? Well, that's what's relevant to, say, the structure of a nucleus at rest in a detector waiting for dark matter to hit, or to the structure of a proton that I'd like to understand from first principles. So we can't do these sort of analytic approaches using perturbation theory. What we can do is numerical. It's an approach called lattice QCD, which is, in fact, exactly what it sounds like. You take the theory of quantum chromodynamics, the strong interaction part of the standard model, and discretize it onto a space-time grid or lattice in 4 dimensions, 3 space, 1 time, in such a way that you can solve the equations numerically. Now, what that looks like in practice is doing very, very high-dimensional integrals. Integrals in as much as 10 to the 12 to 10 to the 15 dimensions numerically. That is an extraordinary computational challenge. Most of the approaches that you would use to do a very large dimensional integral numerically won't work in this context. Things like Monte Carlo sampling, you can't just randomly sample in such a high-dimensional space. So what you do is something called importance sampling, and the underlying idea is you sample more important contributions to the integral correspondingly more and less important contributions correspondingly less. Why should there be more and less important contributions? You can understand simply from quantum mechanics. In quantum mechanics, we know that the path near the classical path is in some sense dominant, and other paths are important, but less so. It's the same underlying idea in a quantum field theory. There's a very well-defined mathematical way of defining which contributions are more and less important and by how much. That allows you to do an efficient set of sampling and then do these calculations numerically. Something very important to emphasize here is that this is well controlled. There are no approximations involved, and importantly, there is no sense in which, if you want to study a nucleus using this method, no sense in which you have to model that nucleus as a collection of protons and neutrons. Nuclei are collections of quarks and gluons defined in the equations of the standard model, right? The free parameters in this lattice approach are the same free parameters as in the standard model, as in QCD itself. Once you fix those free parameters, and you have to fix them by matching to some number of experimentally measured inputs. For example, you fix the masses of the quarks by matching to experimentally measured masses of fundamental particles. Once you fix them, one additional parameter to fix that controls the lattice spacing of your grid, or equivalently the strong coupling that we talked about before. Everything else is a prediction of the theory. From details of the proton's internal structure in terms of quarks and gluons through to nuclear reactions that you calculate. There is no modeling involved. These calculations, as I sort of hinted, are extraordinarily computationally expensive. It would take, some of the calculation I'll describe would take, let's say, 300,000 years on this laptop. It's a new laptop. So on a modern laptop. We don't do them on my laptop, obviously. So we use the largest supercomputers in the world, and many of these calculations, you get to feel a little bit like an experimentalist. You collect data for sometimes years, right? You blind the data, and then 5 years later you can unblind and analyze it. So they really are long-term computational projects to calculate some of these theory quantities. And yet it works. So within the last, it's really been the last 5 to 10 years that we've reached a precision era for this sort of approach for at least simple aspects of, say, the structure of the proton. And in that era has emerged a beautiful synergy between theory and experiment. So here are a few examples from the beginning of this precision era, so from about 10 years ago. This figure is showing the difference between the proton and neutron masses. Now, that's critically important. The neutron is ever so slightly heavier than the proton. If that was reversed, the proton could decay, that's the nucleus of the hydrogen atom could decay, stars wouldn't last for, I don't know, more than a century after their formation, life as we know it wouldn't be life as we know it, right? Small, but absolutely critical mass difference. You can measure it very precisely experimentally. But through theory calculations, you can see how that very precise small difference comes from the delicate interplay of the strong interactions, QCD, pushing it one direction, the electromagnetic interactions described in the standard model by the theory of QED, pushing it the other way, giving a cancellation that precisely reproduces the value that you can measure experimentally. So one example of the synergy between theory and experiment is you can measure something experimentally, but with theory calculations, you can really understand where that comes from our fundamental physics theory. A second example, this figure shows the spectrum of heavy hadrons. So these are particles like the proton, but with some heavier quarks in there. Each of these blue points comes from a lattice QCD calculation. The red bands here are experimental measurements. You can see nice agreement here. This one here, I photoshopped on that red band after the fact. That state couldn't be found. There was a first principles lattice QCD calculation that said it was here. Then the LHCb experiment at CERN went and looked for it there and found it, in fact, exactly there. So predictive calculations that inform experiment. Again, synergy between theory and experiment. All right. So I want to get a little bit more modern. As I said, that was about 10 years ago. I want to tell you about some recent developments in just the last couple of years, especially concerning the proton's pressure distribution. So what do we really know about the quark and gluon structure of the proton? Now, the simplest questions we can ask, we can now answer very precisely. And by simplest questions, I mean we have a proton, and it's made of some number of quarks and gluons, some number meaning an ever dynamically changing number as quark-antiquark pairs bubble up out of the vacuum and then annihilate, right? But we can say, well, how much of its mass, how much of its momentum, how much of its spin comes from up-type quarks or down-type quarks or strange-type quarks? And now, within the last 5 years or so, we can in fact compute the answers to these questions. This is the proton's momentum decomposed into a contribution from up quarks, down quarks, strange quarks, charm quarks, gluons, and all of the pieces add up to 100% as they must. Okay? These questions we can answer, but we can get even more deep into the proton structure and say, what about the three-dimensional distribution of quarks and gluons inside the proton? What about properties of the proton, like its internal pressure distribution? Okay. And in talking about this, I want to emphasize that there are some fundamental and even qualitative questions. This is very satisfying to me, that there are qualitative questions that we're only beginning to be able to answer and have answered in the last couple of years. One of those questions is, what is the gluon radius of the proton? Now, if you go look up in the internet proton radius, right, you'll find a number, and that is what's called a charge radius, the radius of the proton as seen by an electromagnetic probe. Gluons do not couple directly to electromagnetic probes, quarks do. So in some sense, that number that you look up is a quark radius of the proton. It tells you about the distribution of quarks. What about the distribution of gluons, the force carriers of the strong force? Should a gluon radius, defined in some sensible way, be smaller, larger, the same? So we do what we always do as theorists. We turn to models and say, okay, what do models tell me? If I'm from MIT, you like the MIT bag model. That's a model where gluons expand to fill a bag. And you say, okay, the gluons are filling the whole bag, so a gluon radius will be bigger than the quark radius. If you like constituent quark models, that's a model where the gluons basically hide inside massive quarks. The gluons and quarks are always in the same place, so a gluon radius would be the same. If your picture is, well, gluons only exist in flux tubes. When you pull quark-antiquark pairs apart, the gluons are what's pulling them back together, so you get these flux tubes between them. Well, then the gluons are always between the quarks, and the gluon radius should be smaller, right? So models give you different intuition on this qualitative question. Now, one way of defining a consistent definition of a quark radius and a gluon radius is via the pressure distribution inside the proton. Now, let's draw a cartoon of the proton's pressure distribution. This is the center of the proton, and here I'm moving out radially from the center of the proton. This is that radial distance squared times the proton's pressure. I'm showing this quantity because the proton is stable, right? Which means that if there is some outward pressure, there has to be some inward pressure. If there's some repulsive force, there has to be some confining force. And this particular quantity is the one that has to integrate to 0. So on this plot, if there's a hump, there has to be a corresponding dip, right? So that's why I'm showing this. And so if we draw a cartoon, it has to look something like this. If it goes up, it has to come down. It could go down first, then come up. We could have 2 humps, but it has to be approximately something like this, right? We can start to ask questions about this cartoon. We can say, okay, what's the peak pressure inside the proton? Is it more like a bike tire, that's 10 to the 5 Pascal? Is it more like the interior of a neutron star, the densest known object in the universe, that's other than black holes? That's 10 to the 34 Pascal. What is the radial extent of the pressure distribution? Can we use that to define a proton radius? Is it similar to what we normally think of as the proton radius? And importantly, this is a quantity where you can separate out quark and gluon contributions in a very systematic way. How do quarks and gluons contribute to this, and are the radial extents of the pressure distribution similar or different? Okay. Now, a few years ago, we were able to get a first hint of answers to these questions. Now, this is, again, a beautiful example of synergy between theory and experiment. There was a first experimental measurement of the quark contributions to the proton's pressure distribution. Around the same time, we were able to do a first lattice QCD calculation of the gluon contributions to the proton's pressure distribution. Neither approach, neither experimental theory had both. By combining them, we were able to see for the first time the proton's complete pressure distribution. And that's what you see here. This is no longer a cartoon. This green is the gluon contribution to the proton pressure from theory. The blue is the quark contribution to the proton pressure from experiment. And the red is the combination. And so you start to see a few interesting things. The peak pressure in the proton is something like 10 to the 35 Pascal. That's more like a neutron star than a bike tire. In fact, that's more like the quark-gluon plasma in the early universe where the protons were formed than it is like a bike tire. You also see, well, this tail of the green seems to be coming out further than the blue. A first hint that maybe a gluon radius of a proton, sensibly defined, might be larger than a quark radius of the proton. However, both of these, the experiment, the theory, there was some systematics not fully controlled. Ideally, you would do a theory calculation of everything and experiment of everything, right? In the last year, roughly, that's in fact where we've gone, and the synergy between theory and experiment has continued. Now, I'm showing here slightly different quantities. This is slightly more technical. These are the underlying objects that define the proton's pressure distribution. They're called gravitational form factors. And to interpret this plot, these are gluon gravitational form factors. This is an energy scale. The Fourier transform of this thing is related to the pressure distribution. So you've seen this before. It was just wearing a different hat. This point here, right on this zero axis, zero momentum transfer, this is telling you the fraction of the momentum of the proton carried by gluons. It's about 0.5. We actually saw that before also on that plot where we decomposed the proton's momentum. So you've seen aspects of this before. Now I'm just showing more information. The points come from lattice QCD calculations of these quantities. The bands are from different analyses of the same experiment that was the first experimental constraints on these gluon gravitational form factors that define the pressure distribution. And again, nice synergy between theory and experiment. The experiment did not have quite enough information to fully distinguish between these two, so there was some modeling input that went into the analysis of the experiment. And as you can see, the theory agrees much better with the orange attempt at modeling than the green or the purple. So in this case, the theory is informing the experimental analysis. So synergy once again. From these quantities, we can do finally what I hinted at a number of slides ago and say, okay, let's define a quark and gluon radius of the proton and see how they compare. And that's what you're seeing here on this slide. Now, let me break this down. This is the charge radius of the proton, this value here on this curve. That's what you normally think of as the proton radius. Then here, mass and mech are two different definitions of a radius of the proton defined from the pressure distribution, essentially, a mass radius and a mechanical radius defined from longitudinal forces and from energy densities. The red here are quark radii, and the green and the blue are gluon radii. So in both cases, the red is smaller than the blue. The red is smaller than the blue. So this is really, and this is all, and the red and the blue are all from first principles controlled theory calculations, sort of confirming that hint we had before that by this definition, the quark radius is smaller than a gluon radius. What's being highlighted here is this. It was actually one of my PhD students' thesis work was to calculate this number, and a couple of weeks, maybe 1 week after her results came out, there was the first experimental measurement, which was this gray point. That was an incredibly satisfying way for her to meet her defense that her prediction had been confirmed. This is a prediction we're still waiting for an experiment on. And these three, the purple, the orange, and the green, those correspond to these purple, orange, and green curves on this plot. So again, you've actually already seen that data, different analyses of the same experiment to be compared to that blue point. Okay, so first insights into gluon radii of the proton and the pressure inside the proton by combining theory and experiment. It's very exciting to have this time where theory and experiment are really in lockstep, and you can make predictions that get tested on the timescale of your own career and not maybe some future student's career. So, pressure. I keep saying pressure. We can calculate pressure in the proton very precisely. What about, you've heard in this series, other examples of pressure. What about pressure inside neutron stars? Maybe if we could calculate the same sort of pressure distributions in nuclei, we could get first principles insight into the equations of state of neutron stars. That would be great. It is really, really hard. The reason that is really, really hard is that the computational complexity of this approach to do first principle standard model calculation grows by a factorial times an exponential as you go to larger and larger nuclear systems. To give you an idea of that, what we're really doing is integrals via sampling, right? The noise, the statistical uncertainty, it grows exponentially as you go to larger and larger nuclear systems. What that means is you have to take exponentially more samples, right, to get the integral to the same precision. However, the complexity of the calculation, the amount of work you have to do on each sample grows factorially. So you have to do a factorial amount of work on an exponential number of samples. And so that means that very quickly you run out of steam. And you can do these sorts of calculations for A is the atomic number, the number of protons and neutrons in a nucleus, for nuclei with less than about 5 protons and neutrons in them, right? And pushing that becomes intractable. No future supercomputer will allow us to push that boundary anytime soon. However, even looking at small nuclei, we can get some really interesting insight into the standard model physics needed for searches for physics beyond the standard model. I want to give you just one example, and that is in the context of dark matter, because this is really one of the big mysteries of our age, right? We have 5 times as much dark matter as normal matter. What is it, and how can we constrain it? Now, there is really abundant evidence for dark matter. This is not at all exhaustive, just a few examples on the slide. This is the Coma cluster. That's a large cluster of galaxies near Earth. And as far back as the 1930s, it was observed that if you only have the luminous matter, like the stars that you can see, it shouldn't hold together. There's not enough mass to hold that cluster together. It's like something else is acting gravitationally to hold the cluster together that you can't see, something dark matter, right? This is a beautiful false color image of the bullet cluster, where you can really see clusters of galaxies collide. So the blue is matter that you can infer is there from gravitational lensing. So that's mass that interact gravitationally. The pink is that you can see there from luminous matter, like stars. And the interpretation of this separation is that you had clusters of galaxies with about equal distributions of matter and dark matter, and they collide, and the dark matter sails through, and the regular matter collides in the middle, and that gives you the separation. And there have been many, many more examples of this being observed since then. Galactic rotation curves. A nice spiral arm galaxy. This is the center of the galaxy. We're moving out along a radial direction. Everything's moving too fast. This is what you observe. If you had only the matter that you can see, the visible disk, it should only be moving like this, otherwise it should be flying apart. Again, something's acting gravitationally to hold it in. And you can go on and on and on, right? There's compelling evidence for something. The best explanation we currently have is that there's some kind of dark matter. So we try to make theories of what that dark matter could be, right? And theorists are very good at coming up with theories. Extra dimensions, supersymmetries, extra neutrinos, extra axions. You can come up with many, many possible explanations. And then we try to constrain that space. Just one of the many ways we try to constrain what dark matter could be is by looking for it terrestrially in detectors that you bury deep underground and look for dark matter to hit. And just one of the kinds of dark matter that you might see in a terrestrial experiment could be called WIMPs, that's weakly interacting massive particles, that is particles that interact through the weak interactions, also very weakly, but through the weak interactions with regular matter, right? We would like to see dark matter hit a nucleus in our detector. Failing that, we would like to say what not seeing dark matter hit in a nucleus in our detector means for the possible properties of these WIMPs, these dark matter candidates, right? Doing that depends on the properties of the dark matter. That's what I'd like to know. The properties of the nucleus, that's what I need to know from the standard model. Okay, now, having not seen dark matter in these experiments, what you get is exclusion plots. And the way to read this is the mass of these dark matter candidates, these WIMPs. This is SI, just means spin independent. This is that dark matter candidate interacting with a proton or a neutron, the cross-section of that interaction. Every experiment gets a line, and the phase space above the line is ruled out by not having seen dark matter hit the nucleus, right? Now, what I want you to notice here is what's highlighted here in yellow. Nucleon means proton or neutron. So this is the interaction cross-section of dark matter with a proton or neutron. However, the experiments don't use protons and neutrons in the detectors. They use nuclei, typically very large nuclei. For example, everything with an X here is using xenon. Right? Xenon has 140 protons and neutrons in it. So to make this plot, there's been a translation between not seeing dark matter hit xenon and what that means for the interaction of dark matter with a proton or neutron, which is the property we'd like to constrain. Now, the simplest way of making that translation is to say, okay, dark matter will hit my nucleus and it will hit a single proton or neutron at a time. This is sort of old school nuclear physics. You use what's called the Born approximation, and you say, I'm going to multiply the interaction of dark matter with a proton or neutron by the number of protons and neutrons, right? Well, what if dark matter interacts non-trivially with multiple protons and neutrons in a nucleus? Because a nucleus is not protons and neutrons stuck together. A nucleus is a collection of quark and gluons, as we know from the standard model of particle physics, right? This here, if you make this approximation, I said we're in the precision era of lattice QCD calculations for the proton. That, you tell me what model of dark matter you like, I go and calculate this to enormous precision. No problem. This here, any corrections that happen because nuclear physics is nuclear physics, right? Nuclei are not just protons and neutrons stuck together without interaction. That is not known. And that is also not something you can measure experimentally for a large class of dark matter candidates, the only way you could measure it experimentally is to do dark matter scattering, which we cannot do, right? So we set out to say, okay, what can we say from first principles calculations about this question? And the answer is surprising, in fact. You see unexpectedly large nuclear physics effects in particularly exactly the quantity that would be relevant to a large class of dark matter scattering from nuclei. Now, we don't know the microscopic theory of dark matter, but the low energy limit of a generic spin-independent interaction is scalar, and so the quantities irrelevant are called scalar matrix elements. Now that's what's being shown here in this plot. This is showing weak interaction matrix elements. That is also a kind of interaction, but it's one that we can measure precisely experimentally, just for comparison. This is showing a percentage nuclear effect, that is the deviation from this Born approximation, where you say nucleus is protons and neutrons stuck together, right? Now, for the weak interaction, in unphysical lattice QCD calculations, because they're incredibly hard, so we can't do them with complete systematic control, you get a few percent nuclear effect. You extrapolate to physical calculations, you get, originally you have a fraction of a percent nuclear effect. You extrapolate, you get a few percent nuclear effect in light nuclei like helium-3. That's 3 protons and neutrons. That matches precisely what you measure experimentally. Once you go to large nuclei with, say, 100 protons and neutrons, like tin here, experimentally, you get tens of percent nuclear effect, right? For these scalar matrix elements, even in the unphysical lattice QCD calculation, you start off with tens of percent nuclear effect. That's 2 orders of magnitude bigger than in the weak interaction matrix elements that we were previously using to guide our intuition on how big the nuclear physics effect should be. What does this mean for xenon? Well, I don't know, right? You would have to do calculations of not necessarily xenon itself, but at least several larger nuclei to be able to match to effective field theories and many body methods to make predictions for what the nuclear physics effects in xenon should be, and say how much that changes these limits set on dark matter properties based on not seeing dark matter hit xenon. Essentially, this is saying you need caution. There are unexpectedly large nuclear physics effects in this quantity that you need to understand from theory. We need to understand the standard model better to find the beyond standard model physics. Okay. And it's not just dark matter. That's an interesting example because we have a hint of something interesting happening there. But are neutrinos their own antiparticles or not? We don't know. We're doing experiments to find out. The way you look for that is through experiments looking for double beta decay, that is 2 neutrons decaying to 2 protons, emitting 2 electrons and 2 neutrinos. If those neutrinos annihilate with themselves, i.e. the neutrino is its own antiparticle, then you could see a neutrino-less version of this decay. It would be great to be able to predict neutrino-less double beta decay rates for different nuclei and say which one is the one we should build gigantic experiments out of for the best chance of seeing it. We can't make those predictions. They're very large uncertainties because we need to understand the standard model better. There are lots of other interesting things about neutrinos. We don't know the hierarchy of their masses. We don't know their oscillation parameters. There's a sort of flagship experiment in the United States called June under construction. And to really analyze this experiment, you need to know what are called axial form factors of argon that has 40 protons and neutrons. Again, theory input we need from the standard model and so on. So sort of all over this map of beyond standard model physics, there are reasons we need to understand nuclear physics better. These are exponentially harder problems. The way to do them is to try to find exponentially improved computational methods. So the hope for first principles nuclear physics is what drives me to the last sort of 10-minute hint of this talk, is how new developments in computing and algorithms are promising to open up that pathway to understanding from first principles, not just the proton in great detail, but also nuclear physics. Okay, so we're talking about first principles calculations starting from equations, right? The standard model of particle physics, fundamentally, it's a set of equations that demand extreme scale computation. You might immediately think about machine learning. Machine learning has really revolutionized a lot of things that demand extreme scale computation. Can we accelerate these calculations that way? Now, let me present just one problem that occurs at the very first stage of every lattice field theory calculation, no matter whether you're trying to calculate the structure of the proton or a nuclear reaction rate. It's essentially just a sampling problem because you're doing a very high dimensional integral. So what you want to do is you want to generate samples. We're going to call them phi. I have a variable x here because I'm going to draw them over some grid of points x with a known probability distribution. It's given in this form, the exponential of the action s. The action here is the quantity describing the quark and gluon dynamics in the standard model. I can write down an equation for what s is. So at the most fundamental level, the first step of every lattice field theory calculus is simply a sampling problem. I want to take high-dimensional samples according to a known probability distribution that I have the equations for. What that looks like, if we were to imagine the samples look like this, they don't, they're somewhat more complex, but imagine they look like this. These ones here, where you see there are correlations on some canonical scale, those are more likely, they should occur more often. This is random noise. That is less likely, that should occur less often, right? I want to sample the more likely contributions correspondingly more, the less likely contributions correspondingly less. Okay, pictured like this, and especially if I draw the samples like this, this has an immediate and clear parallel to a problem that's received a lot of attention in the machine learning community. Image generation. If I can generate samples that look like this and not this, well, that feels like the same problem as generating these fake pictures of people's faces through a facial generation algorithm where you get this and not that. That's just random noise, right? Immediate and clear parallel, also immediate and clear differences. I actually want this random noise, just not very often. I want it, and I want it with a very precise and well-defined probability that must be exact, right? If I'm generating pictures of people's faces, I never want this random noise. And with what probability do I want this face? Well, that's not really well-defined, right? So let's stack up the similarities and differences between these problems. This is a set, also called an ensemble, of lattice QCD gauge field samples that I'd like to generate. This is a benchmark image set for machine learning. Not a particularly state-of-the-art one, but that doesn't matter for this comparison. It is only the full set or ensemble of lattice gauge fields that has any meaning at all. They have to follow a precise probability distribution. Whereas in images, each image has meaning. That particular image is a good picture of a face or not a good picture of a face. Right? The distribution over them is not as important. We have an extreme inversion of the typical data hierarchy. So each sample, each gauge field, is defined by something like 10 to the 9, or all the way up to 10 to the 12 or 10 to the 15 numbers. But you only have order thousands or tens of thousands of samples. In a benchmark image set, each image is defined by, say, 3,000 numbers, but you might have 60,000 images available for training. The ratio of this and the ratio of this are extremely inverse to each other, right? So that means that any approach that involves training data is not an option. We have far more degrees of freedom per sample than we have samples available. Long-distance correlations define physics. In images, local structures are particularly important, and things like convolutional neural networks that have been very successful are really defined because local structures are important, a nose, an eye, an ear, whereas it's really the opposite. It's the long-distance correlations that define the physics in our case. There are complicated symmetries that you can't even mock up in the image space, but I will try to. The simplest are translations and rotations with boundary conditions in 4 dimensions. And so, okay, if this is a gauge field configuration, this is a transform field, just a rotation and translation. These are identical from the field theory perspective. They encode the same physics. They must be generated with the same probability. That you can sort of visualize as an image. But what we really have is our gauge field configurations don't actually look anything like images at all. We actually have, on each edge of a 4-dimensional hypercube, we have matrices, 3 by 3 matrices with unit determinant. And there's a symmetry called a gauge symmetry, under which this is my 3 by 3 matrix living on this edge here. I'm going to left and right multiply that by different matrices in a correlated way across the whole lattice. What that does effectively is it takes, if I start with a configuration where every edge is identical, every edge will end up different. But these are still identical. They still encode the same physics, right? So there are complicated internal symmetries that need to be encoded. And what this makes clear very quickly is that you cannot use any sort of out-of-the-box AI or machine learning tools to apply to this problem. You have to design something from the ground up. Now, the other part that often people wonder about is, well, I keep saying I'm doing first principles theoretical physics calculations, and now I want to put a black box in there. No black boxes. We need to use machine learning in a way that guarantees mathematical exactness and preserves the fact that I'm doing a first principles theoretical physics calculation with mathematical rigor, right? What that means is that the machine learning can do one thing and one thing only for me, and that is get the answer faster. I'm doing an integral. If the answer to my integral is 2, it has got to be 2, whether I use machine learning to get it or not, right? What that means is that we have no room for modeling, approximations, errors, systematic uncertainties. What that means is that I have to create this scenario here. If my machine learning algorithm is poorly trained, I must still be able to guarantee that my results are correct. If my machine learning algorithm is well trained, I must still be able to guarantee that my results are correct, but ideally this will be much faster. And that faster can be the difference between something being computationally tractable and not, right? So how do you do that? Just a flavor. I don't have time to go into details, but just a flavor. There are many ways. 3 examples. First, the boring way, right? Use machine learning to optimize your existing algorithm. That is, I start from the same start, I get to the same finish, that is provably exact theoretical physics calculations, and the same person's running the track, we're just going to make them faster, right? Then you have all the guarantees of your existing algorithm, you've just accelerated it. This is not a very interesting application of machine learning, but it can be very useful. There are many algorithms that have a lot of free parameters to be tuned that don't affect their rigor. You can tune them more efficiently using AI. Okay. More interesting. What if I can change the problem into a different problem that I can guarantee mathematically has the same solution? In this case, I'm using machine learning to do the changing of the problem, not the solving. I'm changing the problem and then using my conventional algorithm to solve. So same person running the track, but machine learning has made the track shorter, right? This can be very, very effective, and there are many ways of doing this. One example is preconditioning of any type. I like giving an example. I want to invert a matrix, and I want to do it faster with machine learning. I will not train an algorithm to say, here is the matrix, give me its inverse. Because if it's wrong, that's useless, right? I will train an algorithm to say, here is the matrix, give me a preconditioner which will accelerate me taking the inverse using conventional means. And then if the preconditioner is bad, the conventional algorithm is just slow, you haven't won anything. If the preconditioner is good, the conventional algorithm is faster and you win. But you've not lost exactness, right? Another example is a change of variables. Even just complex analysis, if you take a complex integration contour and you deform it, as long as you don't cross a pole, you're guaranteed that the answer is the same. You can use machine learning to deform the contour to a place that's easier to numerically do the integral, right? Change the problem, use the same method to solve. A third example is use machine learning to solve a different problem, as long as you have a way of correcting for it being not quite right, right? Any sort of sampling is this. So let's say I would really like to get here, and this means sampling a probability distribution. What if I use machine learning to try to do that? Well, it might not be exactly right. As long as I have a way of guaranteeing I can correct to the right answer, I still have mathematical rigor. And so in my last couple of minutes, just one hint of this last example of how you can actually apply this in lattice field theory. So one example of doing this is to apply to that sampling problem I mentioned, where we want to generate samples of gauge fields according to a known probability distribution. You can accelerate that with machine learning using what's called a flow model. This is a kind of generative AI, if you like. But a flow model is really just a change of variables. It is a map that takes me from one distribution to another. Now, if this first distribution is one that's really easy to sample, think things like Gaussians, uncorrelated Gaussians. You can sample them incredibly efficiently. If the map then takes me to the distribution I actually want to sample from, which is incredibly expensive, well, then you win, right? You sample from the easy distribution, put them through your map, and out come the samples of the distribution you wanted. If this map has certain properties, technically it needs to be one-to-one, invertible with a tractable Jacobian, you can also correct for any inexactnesses in the map not being quite right and maintain your rigor. Now, to do this for QCD, as I said, you can't take generative flow models used in other contexts and apply them. You have to go back to the start. And in particular, as I said, we don't have data samples that look anything like images. We actually have matrices on the edges of this lattice. And what that really means is that I have a compact connected manifold that does not look like the real line. Normally you do machine learning on the real line, right? And so instead of a flow on real numbers, we first had to go back even to the beginning. The simplest compact connected manifold is just a circle. How do you do machine learning on distributions defined on a circle? That's not obvious. You can't just wrap the real line, you get discontinuities at the endpoints, numerical instabilities. Turns out that was interesting not just for us, but also for people who want to design multi-jointed robot arms, because you define their positions by angles, right? So interesting cross-applications there. Once you do that, you have to worry about symmetries, these complicated gauge symmetries. You might have noticed I said you can correct for any inexactnesses. That includes broken symmetries. But if you have a 10 to the 12 dimensional distribution with a 10 to the 12 dimensional symmetry group, that is not something you can learn. You have to embed the fact that you have a flat direction in your probability space directly in the algorithm by designing custom architectures that transmit that information. Once you do that, you can see that this actually works in simple lattice field theories. This is a measure of cost per independent sample. This is a parameter of the theory, which if you like, you can imagine as making a lattice spacing smaller, a limit you have to take. These are conventional sampling algorithms. You can see they get exponentially more expensive moving left to right. A machine-learned sampler remains approximately flat moving left to right. And over here, it's several orders of magnitude more efficient than conventional approaches. That is great. That's a simple lattice field theory. It's not QCD. You have to worry about multimodal distributions, and not just in principle, but in practice, exact sampling in such distributions. You have to worry about quarks. Quarks are particles called fermions, which means they anti-commute. How do you do machine learning with anti-commuting variables? It's not so easy. But once you've figured that out, you can do more complicated quantum field theories. This is an observable. It's called the chiral condensate, but what it is doesn't matter for what I'm trying to show here. This is the number of samples. This is a conventional sampling algorithm. You can see as I increase the number of samples, the uncertainty goes down with 1 over square root n like it should, but the number is wrong. This is the truth. That's because the conventional algorithm is stuck in one part of a multimodal probability distribution, walking around there, and it can't jump the probability barrier. This is a region of parameter space where conventional algorithms can't be used. The machine learning approach converges nicely to the correct result because it's not an update-based sampling algorithm. Samples are independent. And then you have to scale up, and that is the test that's yet to be passed for this approach. Aurora is the new larger supercomputer that has just been turned on at Argonne National Lab, and we are trying to deploy at scale. And we will see whether this can be used for state-of-the-art calculations. It's very difficult. We're trying to scale custom physics-informed machine learning algorithms to a similar scale as state-of-the-art machine learning used in industrial contexts with the budget of a few postdocs. But we will see if it can be used at scale, and the goal is, of course, nuclear physics calculations. So the summary really is that there is provably exact machine learning accelerated sampling algorithms that are orders of magnitude more efficient than conventional algorithms, that are unbiased in regions of parameter space where conventional algorithms fail. And the work now is the engineering work, not the interesting physics part of the work, but the engineering work of how you scale that up in practice to the largest supercomputers in the world. And of course, the motivations. Let's really dig into the gluon structure of the proton, things where you would need an order of magnitude on precision. Let's do nuclear physics for dark matter direct detection for, we did a few years ago the first proof of principle calculation of the first step of Big Bang nucleosynthesis. So a neutron proton goes to a deuteron and a gamma in the first seconds after the Big Bang, after the universe was formed. Would love to go down that pathway, be able to start saying things about lithium abundances in the early universe and so on. We need to scale. Okay, so that's really the end of the story here. A reminder of the story we've seen. So starting from the equations of the standard model, first principles theoretical physics calculations, we're really starting to get new windows on everything from the structure of the proton. Where this example of the proton's pressure distribution, where by combining theory and experiment, we're getting answers for the first time into some things that feel like really fundamental qualitative questions, like what's the gluon radius of the proton, through to first hints at important questions relevant for searches for physics beyond the standard model, like dark matter direct detection. And looking to the future, there's a new generation of provably exact physics-informed machine learning algorithms that is promising to redefine what the limit is for these kinds of approaches. Thank you so much.